So today we'll talk about something called kernel computation. And this is kind of the first of our lectures on software. So we already talked about, we started by talking about hardware. We talked about architecture, efficiency, comparing different chips. Then we did a complete shift to neural networks and how we can optimize neural networks without necessarily knowing much about the hardware itself. We're just optimizing the number of operations and the size of those neural networks. And now we want to move on to a next kind of critical component of actually running these deep neural networks or deep learning workloads, which is software. And it's often kind of overlooked if you're using kind of, PyTorch, or you're thinking about a GPU. You usually don't think about the stuff in the middle. Like you often take it for granted, but it's actually really hard to do and really important as well in kind of the performance of neural networks. And I would say that's kind of one of the main reasons NVIDIA is on top right now, because they have a really good software stack. So I don't know if you guys follow this kind of news, but GraphCore, it's a British company which is creating an AI chip called the IPU, Intelligent Processing Unit. I don't know, I don't remember what it stands for. But it's basically everyone thought, once these guys will benchmark their numbers, then they will blow NVIDIA out of the water. It will be much better. There's no question about it. And what happened was actually when they benchmarked their numbers, they were slightly worse than NVIDIA in all of the metrics. And so you read all the analysis articles on this kind of thing, and it was saying basically their software isn't there yet. And that is much harder to do than the actual hardware. That's why they're behind. And so, so never underestimate software. That's how companies kind of go under in the chip industry. So what will we talk about in software? We'll talk about mapping operations to hardware devices. We'll talk about compilation, and we'll talk about different kernel implementations. And so what that means is, given a simple piece of code like this vector multiplication, or if the A's and B's are vectorized here, then matrix mul, then how do we actually run this on hardware? What are the different algorithms for doing that? How do we map it to the processing elements and so on? So the question we're trying to answer is, how do we optimize these fundamental deep neural network primitives onto our hardware? And this is a very simple view of the machine learning software stack. I think it's the most relevant view for a machine learning user or a deep neural network designer or someone who runs neural networks. But it basically, usually what you see is PyTorch or TensorFlow or something up there. And obviously that runs on top of Python. So it's a Python library where you're calling Python functions. But then what does Python call? So depending on the hardware, it calls different things. And currently it calls a library called cuDNN if it's going to run on a GPU. And cuDNN is written in CUDA. So CUDA is a C-based programming language which runs on GPUs, right? If you are running this on a CPU, an Intel one, it usually calls a library called MKL. So that's Math Kernel Library. And then it has this extension called DNN. So it usually calls MKL DNN, and that's written in C++. And everything below that, I think we're not really interested in because it's standard. It's the same across different kinds of programs. But this part is quite interesting to us. And so if you just Google the cuDNN documentation or the cuDNN API and you start looking through their functions to kind of see what granularity they have their implementation at, it's something like this. So they implement the whole convolution, for example. So now when you think of PyTorch, think of it as just a wrapper for cuDNN if you're running on a GPU, basically. And so that's actually all it is. Of course, it has some other stuff kind of in presenting a nice and usable API, but the performance it gets is usually by using the latest cuDNN functions. So in this lecture, we want to look at different algorithms of implementing matrix multiplication. So matrix multiplication, I can implement it using for loops very simply. But how else can I implement it? And there are many different ways, usually called transformations or kernel implementations that we can do to the matrix operation to make it more efficient in some cases. So we'll look at some of those, and we'll look at the convolution as well for some of those kernel implementations. So we'll start with something called Im2Col, image to columns. We'll talk about Strassen's transform, Winograd transform, fast Fourier transform, and log domain multiplication. So these are kind of kernel implementations of matrix small and convolutions where you don't change the result, or you don't change the final result by much. You're not approximating the matrix multiplication. You're just performing it using different mathematical operations. We'll also start looking a bit about approximations of matrix multiplications. So in that case, we are actually not doing the exact operation anymore, similar to pruning, where we're approximating an operation with a pruned operation. Here we will approximate an operation with something called a low rank approximation of that matrix. And so we'll start talking about that, and we'll give a very brief overview of tensor decomposition as well. And throughout kind of the next few slides, you'll find me saying we saved one multiplication, but we're replacing that with 10 additions or something like that. And so whenever I say that, just keep in mind that multiplications are way more expensive than additions. So in this case, about 4 times more expensive. And so keep that 4-to-1 ratio in mind when I say these kind of things. I think even at int 8, they're even more efficient. So maybe 0.03 to so it's more than 4 times. So 4 to 10 times or something more efficient. Well, not 10, 4 to 8 times more efficient. Okay, now let's start with the first transform. Any question about the motivation or kind of why we're looking at this so far? No. Okay. So Im2Col. So Im2Col is a way to implement the convolutions on most kind of commodity hardware. And what does that mean? So what Im2Col literally means is transferring an image from a 2D image to columns in a matrix, right? And so, for example, for this convolution here, we have a filter, and we have a feature map, and we have the output. So basically, we need to sweep that filter across the feature map to get the output, right? So the first filter will be convolved with this piece of the input, and then you'll get this output. But convolution is not kind of natively supported in most commodity hardware, right? You would have to transform it into additions and multiplications and so on. And usually matrix multiplication is very well supported actually, and most hardware is built so that matrix multiplication is implemented really efficiently on it. And so how do we transform this convolution into a matrix multiplication? And so what we can do is we can flatten the filter. So instead of being kind of a 2D shape, it can be a 1D vector. And then for each window of the feature map, we convert the image to a column. So the Im2Col part is just this transformation here, where we will take that window and create a column in our matrix from it. And so by doing matrix multiplication, in this case, the vector-vector multiplication, we can get the same output as we got here. Then as we sweep the convolution window, we take the next window, and then we put it as a new column of our new kind of transformed image. And we keep doing that. So the next window and the next window. And so what this gives us is kind of it transforms our convolution into a matrix multiplication. And it's very simple, but it's basically how most convolutions are implemented on GPUs. Because GPUs again don't support natively convolutions. So how would you implement it? You need to transform it into a matrix multiplication, which is really well supported and really well optimized. Can someone tell me what would be an example of hardware that does support convolutions natively? So can you think of anything? So hint, we looked at that hardware. Sorry. An image processor may support that natively, but not that I know of. So I mean, TPUs, for example, or kind of these purpose-built chips would actually support that natively. And usually the way they do that is they have a wait stationary data flow, right? So they would get that filter, they would store it in kind of these PEs. And yeah, Yunzo already replied as well on the chat. But yeah, basically you would get the filter, you would store it in the PEs, and you would leave it there. And then that wait stationary data flow, you would pass different inputs across that filter, and you would get the result. So, so why is that natively supporting convolutions as opposed to a GPU or a CPU? Is because the hardware was built for this operation. The same is true for NPUs in mobile phones, for example, where you also have kind of a specific cache to hold the filters in a convolution operation. The same was true for the DLA that we designed back at Intel, where the hardware is built for a convolution. And we actually did the opposite. When we had a fully connected layer, we converted it to a convolution. So this transform can go either way if you think about it. So yeah, but IM2Call is very relevant right now because most hardware is more general purpose, and it doesn't have native support. It doesn't have this assembly instruction or VLIW instruction which says do convolution. Yep. Yeah, so that's a good question. So turning the image into columns has no computational cost, right? Because it's just reorganizing the memory, but it has. So that's kind of leading on to the next slide, where not this slide, but it does have a memory cost, right? So so what would be the memory cost? That's a good question. Yeah. Yeah, exactly. So so as when he pointed out, we are replicating the data, right? So we're using up more memory bandwidth or more on-chip buffer to make sure that that data is replicated. And again, that's why we looked at all of these wait stationary, activation stationary, whatever data flows to avoid this kind of replication. It also it seems that the access pattern for your data would also be a bit more complex, but usually people do that IM2Call kind of as an offline step almost. So they would reorganize the data before it goes into your convolution operation, so that these accesses actually fit really well in the cache and so on. And this is actually something that you will optimize during your next assignment. So when you're implementing or when you're optimizing different operations on GPUs and CPUs using TVM. So IM2Call also can work on the filter. So it doesn't have to just be the image, 2 columns. We can also do it on the filters. Although this is much less common because it introduces all of those zeros. But basically, we can flatten the image in this case, or the activation map, or the input feature map into a vector. And then we can replicate and pad the filter in such a way that when you do vector matrix multiplication, then you would get the same result at the output. So in this case, our first window is 1, 2, 4, 5. So if we multiply this, 1, 2 will multiply by 1, 2, and then 4, 5 will multiply by 3, 4. So it would still work out. So, so what is one problem with IM2Call? We already kind of covered that through Aman's question, but data replication at the algorithmic level is expensive and may increase the demand for external or internal memory bandwidth or storage, basically. Okay, so that's IM2Call. People kind of colloquially refer to IM2Call as convolution to matrix mul conversion. But the IM2Call algorithm itself, if you call it from NumPy or something, is just that conversion, that memory reorganization. That's all it does. Now let's look at another transform And this is where we'll start, counting multiplications and additions and see how much we saved through each one. And so on the left here, I'm showing just normal matrix multiplication. So you have this A matrix multiplied by the B matrix, and what you do, you multiply the rows by the columns and you add the partial products, and that's what you get: AE plus BG, AF plus BH, and so on. So you get in total 8 multiplications and 4 additions. So someone called Strassen said, I can do this in a better way. I don't need 8 multiplications. I just need 7 multiplications. And so that's what he came up with. He said, if we create these partial results, K1 through K7, we can actually compute this in 7 multiplications and 18 additions instead. So he saved 1 multiplications and he gained 14 additions. It's arguable whether that's better or not. As I said, there is a big ratio between 4 to 8 in the energy efficiency of multiplications versus addition. It varies by the precision as well. So multipliers grow quadratically with the input size, at least integer multipliers, whereas adders grow linearly. And so this on many hardware types would actually give you a lot of savings, or some savings. In deep learning and in deep neural networks, we also have an extra trick, because some of these multiplications or subtractions and additions can actually be done offline, because some of these correspond to our parameters. And so if we're doing this during inference, our parameters, let's assume that the B matrix here is our parameters or our weights, then we can compute those things offline. So not during inference. So I can compute it once, deploy it to 1 million devices, and run it there with just 13 additions instead of 18. And so so that's one example, a trick of kind of speeding up matrix multiplication. So another one which is quite interesting, but now actually, are there any questions about Strassen's transform? Did it kind of sink in? Does it make sense? We can go through kind of all of why this works and so on, but it's just reorganizing operations literally. For example, if you factorize this in a certain way, then you can transform one to the other very easily by just changing where the additions and subtractions happen and so on. So questions in real land or online? Okay, so another transform which is really interesting, and we actually use that one a lot when designing our accelerator, is Winograd transform. And now we're not talking about matrix multiplications anymore, but we're talking about convolutions. So let's take a look at an example of a one-dimensional convolution. We have a filter denoted by F0 to F2, and we have an input that's kind of very long, but let's take a tile of that input, I0 to I3. And so we need to sweep that filter across that activation map or that input. And if we write that in matrix form, it looks like this. So first we multiply the filter by I0, I1, I2. And then we sweep the filter one step and we multiply the filter by I1, I2, I3, right? So that's the definition of convolution. Taking a filter, this is a one-dimensional convolution. We're just sweeping the filter across the input, and we're just writing that in matrix form here. And so how many multiplications and additions does that take? It's 6 multiplications and 4 additions. So a person called Winograd came around and said, I can do this better. And it's in the same kind of spirit as Strassen's transform, but now he's also leveraging the fact that there are common pieces of data in that matrix. So that matrix doesn't have all unique values or is not unrestricted. It has each one of its rows is a shifted version of the row before it with one new value, and the rest are old values in the case of stride 1, for example. And so he also reorganized the computations there, and he proved that this is the minimal way, this is the minimal number of multiplications required for a convolution window to do the same exact operations. And so again, he has these equations where he reorganizes, the normal operations that you would have done here, like I0, F0 plus I1, F1 plus I2, F2, into these intermediate values K. And you compute it using this equation. So things to keep in mind with the Winograd transform. And actually we can do the same trick, right? So some of these results can be computed offline. So we can even reduce those number of additions further. So in this case, we go from 6 multiplications for additions to 4 multiplications and just 8 additions if we leverage that fact. And yeah, so yes, Aman. So that's a good question, whether the transformations scale to larger inputs. So we will talk about that for Winograd, but for Strassen's transform, in general, I think the larger the input, the more savings you get, if I'm not mistaken. So it does scale quite well. And I think people usually do Strassen's transform for very large matrices. And that's why you don't actually see that much in deep learning. Because matrices aren't that huge, at least not offline filter matrices, which are usually what we target for these transforms. Yeah, so. Actually, we target both. We don't just target the parameters, but I think it works better for larger matrices. So a few comments about Winograd. So typically, the larger your convolution window is, the more savings you can get. So for a 3x3 convolution, I think this is the one we implemented in DLA, was that you would get like 2.25x reduction in multiplications. So the example I showed before for a 1D conv, it went from 6 to 4 multiplications. In this case, it would go from like 9 to 6 or something, or 9 to 4, something like that. So it really reduces the number of multiplications. However, one thing to keep in mind is, especially if you're creating custom hardware for Winograd, is that the transform is specific not just to the filter size, but also to the size of the tile that you're operating on. So what I showed in that previous thing is, a tile size of 4 and a filter size of 3. So the numbers to transform into Winograd domain would be very specific. So these computations would be very specific to that size. If you're changing the tile size, so this matrix now has, a bigger tile size, then it wouldn't be using the same computation here. And people have generalized that computation by writing it in matrix form instead of writing it out using these equations. And we won't go through the matrices, but you can find them in the paper. But basically, you transform your input and filters with these G and B matrices. And then you can undo the transform through these A matrices at the output, right? So you sandwich your operation with these A matrices and A transpose. And what these matrices are doing when they're multiplied by the filters and multiplied by the input, they just transform them. They basically do a generalized form of these equations. But one thing to keep in mind is obviously these G, B, and A are very unique to each of your filter and tile size. So if I create custom hardware for this and I want to embed this transform in my hardware, then I can do it for just one size of the convolution. If I do it for another one, then it needs to be configurable, and that has its own overhead as well. And the real savings from Winograd transform actually come from the fact that once we transform our input and filters, it's not a convolution operation anymore. It becomes an element-wise multiplication. And so after kind of applying all of these transforms, then we don't need to do a convolution. We don't need to sweep the filter across our inputs many times. We just do a multiplication instead. Also, one thing to keep in mind again is that these filters, they can be transformed offline, so they don't need to be done online. but multiplication by these b's, so transforming the input, needs to be done online while you're performing your inference. And these a's as well, to undo the transform, need to be done online. So one note of caution, and this is actually something we found empirically as well with these transforms, is that when you're using lower precision, so let's say I'm using int8 precision for my numbers, then the transform itself is usually much less robust to lower precision. So multiplying by those g's and those a's and those b's are you would lose more accuracy if you do it in lower precision. So usually what people do to overcome that is that they do the transformation in high precision. They would do this element-wise multiplication in the lower precision. So usually FP16 and int8 or something like that. And this is not just true for Winograd. I mean, the empirical results I saw were on Winograd, but it's also true for other transforms that we're talking about. So performing that initial transformation is typically done in higher precision for that reason. Okay, any questions so far? So now you should know Strassen's transform and Winograd transform. Does it all make sense? Is it? Okay. Now FFT transform. So who here remembers what FFTs are? I hope everyone, no? So, or FTs, just Fourier transforms, discrete Fourier transforms. So, okay, so I mean, Fourier transformation is one of the most important transformations on Earth. It's basically going, you must have taken it in kind of a digital signal processing course where you're going from a time series signal to the frequency components of that signal, right? And so usually it's done, let's see, usually it's done, this is kind of the equation for discrete Fourier transform, but you multiply the input with this exponential of, you know, yeah, with this exponent basically, and you sum up over the size of the input. And so it's basically, you know, this transform and this inverse transform gets you from traditionally the time domain to the frequency domain. And usually the, you know, the common examples are, you know, you have a sine wave signal in the frequency domain, so this is time, and then you have frequency. I think the sine wave is like this, I may be wrong, and then the cosine is, you know, symmetric or something like that. And so that's kind of done through Fourier transform. And in its, and this is for continuous function, what I'm showing on the board here. So for continuous functions, there's an integral here, whereas for discrete functions, we can use a summation. And so what are we doing here? We're transforming the weights or our filter and the input through Fourier transform. And then again, the convolution theorem states that, you know, if you do convolution in the time domain, it's actually equivalent to multiplication in the frequency domain. So it's quite similar to Winograd transform in the sense that, you know, you're replacing this computationally heavy operation of convolution with element-wise multiplication. But what are you paying as an overhead? You actually need to have same size, you know, tensors or same size matrices in this case to be able to do that element-wise multiplication. So what we end up doing is actually padding this filter with all zeros to be the same size as the output feature map in order to perform this element-wise multiplication. And so, yeah, so if you're doing the convolution normally, you're sweeping a filter size, in this case, a 2D filter of size R times S on an image with output dimensions P and Q. And so the total number of operations will be something in the order of RS times PQ. So once you do the Fourier transform, this becomes a multiplication. but you're also increasing the size of your filter. And so in this case, it becomes p times q times binary logarithm of p times q. So it goes from, if p and q and r and s were all the same numbers, it goes from n squared to n log n, basically. So it scales much better. But obviously the condition here for a speed up in the actual operation is that r times s must be bigger than the logarithm of p times q. So if your filter is way smaller than the output size, and it's still smaller than the log of the output size, then you won't get a speed up actually in this case, and you will have also paid for the transform overhead, which is not trivial as well. So so yeah, for all of these, for this specific transform, you don't always get a speed up. It really depends on your dimensions. It also depends on the transform overhead as well. Okay, any questions? Feel like I'm going a bit quickly through these transforms, so stop me if you have any questions. I think reading through them in the book chapter as well afterwards will kind of give you a bit more clarity. But you can also ask questions now. Okay. All right. So I mean, all of the transforms I talked about so far are ways to implement either convolution or fully connected layer. And so if you think back to that, cuDNN library that we talked about in the beginning, you will find different function calls for those. So you'll find con forward 2D FFT, con forward 2D Winograd, and so on. And so there will be implementations in the cuDNN library for all of these kind of transforms. This is another transform, which I think is not supported in cuDNN now, but maybe soon. And so, so what is log domain multiplication? You have two numbers that you want to multiply, a times b. I can write those as 2 to the power of x times 2 to the power of y. If I can find a way to transform, the a's to 2 to the power of x and the b to the 2 to the power of y, right? And then again, in that case, this is a multiplication, but in the logarithm domain, to do that multiplication, I just need to add the exponents because now I have a common base for them, right? And so then you would get the result 2 to the power of z. And so this is basically log domain multiplication. If I can find the conversion from a to 2 to the power of x, if I can find that x value, then I can do an addition instead of multiplication, right? And so how can I find that x? If I have a number a, and I want to transform it into 2 to the power of x, how can I find the x? Yeah, okay, good. People are awake. So basically, you just take the logarithm with base 2, right? And so that's what we do. So to transform into the log domain, we take our inputs, we take the binary logarithm of them, and then we get those x's and y's. And then now we don't need to do a multiplication anymore. We can do an addition and get our z's. And then after we get the z, we can do, 2 to the power of that number, and we get the final result again. And so this is really nice because, if multiplication grows quadratically with the bit width and it's much more expensive, it's 4 to 8 times more expensive than additions, then this can just be a simple way with a single operation to transform, my inputs and my outputs into to and from this binary domain, and then or this log domain rather, and then I can do addition instead of multiplication. So instead of counting the number of multiplications and everything, I actually got rid of all of the multiplications. This is great, right? So one of the main one of the issues here is, what about negative numbers? What do I do with those? I'm sorry? Yeah, so that's a good question. So the converting, actually finding the log of numbers with high precision is not efficient. So that's one problem, and even the exponent. So exponent is also quite expensive. It's more expensive than a multiplication for sure. And so that's one of the issues. Another issue is, what about negative numbers? What do I do with those? How can I take the log of negative numbers? What do you think? Come on. I'm sorry? Yeah, so that's a good point. You don't actually need to take the log of a negative number, right? So you can just basically convert the magnitude of the number using this transformation, then compute the sign offline. So, or not offline, but in a separate computation, where it's usually just the XOR of the two signs of the inputs. Right? And so what is the current problem with log domain transformation? Aman already touched on this. The transformation itself is expensive. But can you think of another problem? So James. It's easy to overflow. Can you give an example? Oh, I see. So you can represent more numbers in the log domain because it compresses your numerical range. And then when you convert back, you can easily saturate the output, right? It may be possible, although I will say, I mean, the operation itself shouldn't change your numbers, right? It's just a way of executing a multiplication in an efficient way. You can think of it that way. So if you were going to overflow through a log domain multiplication, I think you would have overflown anyways with a normal multiplication. So yeah. So when he Yeah, so precision could be an issue as well, because actually um, it's an issue for log domain, and it's an issue for all of the other transformations, just because you're remapping your numbers into a different kind of domain, especially with the log domain where you're shrinking that domain, then you might need higher precision for the initial numbers before the transform. So that's also true, yeah. And I mean, one of the issues is, I'm never just doing multiplication, right? I'm always doing multiply and add. So how can I add two numbers in the log domain? I mean, there is no straightforward way. So if I have those, 2 to the power of x and 2 to the power of y, I can multiply them, but to add them, I need to kind of convert back. And so that's one of the issues. Conversion is costly, and I can't reduce my numbers before doing the conversion back to the normal domain. I need to do a conversion for all of these partial products before I do an addition. And that has been the main reason people don't use log domain multiplication, even though it's so attractive. It is actually, even if we need to use a bit higher precision, even if there is a bit of accuracy loss that we need to retrain for or something, it's actually transforming all of my multiplications to adds. I mean, this is amazing, right? And so why haven't people actually done this? It's because I can't add two log domain numbers, not efficiently. There are so many approximations out there, but they lose a lot of precision in some cases. They're expensive and they require specialized hardware in other cases, so you can't implement it on GPUs or things like that. And so that has been the main issue so far. Good news though, digging through kind of NVIDIA's patents, they seem to be working on it. And so I found this patent, which I will look through it first, but I think I'll get you guys to implement it in assignment 4 because it's quite interesting. So they actually found a way to add log domain numbers quickly instead of converting back to the linear domain. So they describe it in the abstract here very simply by decomposing exponents into separate quotient and remainder components, sorting the quotients based on the remainder, summing the sorted quotient. So it's a whole kind of, it's a big math trick, basically. But they actually made it work, it seems, at least from this patent. There are no publications on it yet, but there is this patent. So I'm guessing in the next generation of GPUs, you will see someone talking about log domain fused multiply add. which would be really cool. So this was one of the main issues. People are really focusing on it. They're trying to solve it, and hopefully you guys will implement it. So how do we select which transform to use? So what do you think? I'm sorry? Ask NVIDIA. Okay. So I mean that's a good approach, because that's actually what happens on GPUs. Again, digging through the cuDNN library, you'll find this function, cuDNN find convolution forward algorithm execution. Basically, this function attempts all algorithms available for conv forward, and it will provide kind of the runtime for each one. And so that's why whenever you're benchmarking a model on a GPU, you kind of discard the first few runs, because like through training, for example, you discard the first few mini batches or something, because at the beginning, what NVIDIA is doing, or the cuDNN library is doing, or PyTorch maybe at this point is doing, is it's trying all of the different transformations for each of your convolutions and each of your fully connected layers. It's seeing which one is fastest, and then it will continue training with that one, or continue inference with that one. And so there isn't really a good heuristic, and sometimes it's just too complicated to compute it by hand, even though you can count multiplications and additions for many of those. But yeah, so there are these benchmarking functions in the library itself to just find the execution time for each kind of implementation. Okay, so we talked about a bunch of kernel implementations, and this will actually be the topic of your assignment 4. So the last assignment, the next assignment is assignment 3. It will be on compilers, which we are preparing now and will be released hopefully on Monday. But in assignment 4, you will go and implement all of these transforms by hand, which I think would be a really cool exercise. Now let's talk very briefly about approximation of matrices. Instead of finding new ways of implementing the exact operation of matrices, let's touch upon low rank approximation of matrices really quickly. And when I say low rank approximation, do people know what I mean, or not really? No? Okay. When I say eigenvalues and eigenvectors, do people remember? Okay, good. And so basically, eigen decomposition is, finding the, basis vectors of a matrix, for example, and what the scale of each of those basis vectors is. Eigen decomposition, I think, works for very specific matrices. I think they have to be square matrices, if I'm not mistaken. And the generalization, you can think of this as a generalization of eigen decomposition for any size of matrix. It's called singular value decomposition. And so what is happening here is you have a matrix, M, the dimensions are M times N. I can decompose it into a matrix U, a matrix sigma, and a matrix V, transpose. And so U and V here are, if I click maybe, yeah. U and V here are called the orthonormal basis vectors of that subspace. So similar to eigenvectors, these are now the analogous thing to that. They're my basis vectors for the subspace, and these singular values are the scale values. So this is a diagonal matrix, everything else is 0, and each one of them is similar to the eigenvalue. It is but here it's called the singular value. And so even if you don't remember what eigen decomposition is, then this is basically, you take a matrix and you transform it into 3 matrices. So how does that help me? I used to have 1 matrix and I thought that was too much computation. How does transforming it into 3 matrices help me? Okay, I'll tell you. So basically, what we can do next is there's a very nice property for those singular values. Again, the analogous thing to eigenvalues. They tell me the importance of each of my basis vectors. They're the scale value. There is how much does this basis vector contribute in constructing my matrix, right? When I multiply those things together. And so what I can do is that I can actually remove the small ones. So I can remove the smallest, you know, singular value without affecting the reconstruction of M. So I removed one here, then I can remove another one and remove another one. And basically, I can start removing those smallest singular values whilst minimizing my reconstruction error of that matrix M. And so what's happening here is that I'm decreasing they call it a low rank approximation because I'm decreasing the rank of that matrix. I'm decreasing the number of basis vectors that I need to represent that matrix or reconstruct that matrix. And so every time I remove one of those singular values, I can remove a corresponding row and column. And so now my matrix has become, this much smaller computation of matrix, scalar matrix multiplication. So does that make sense? So yeah, sir. No, it's not linear. So usually you can remove kind of the bottom, I don't know, 50 or 60% of the singular values, and you would lose like, I don't know, 2% in your reconstruction error of the matrix or something like that. So it's not linear. But it's not, there is no hard rule here. It really depends on your matrix. People have said that, the matrices in deep neural networks are fundamentally low rank. They don't need that much representation power. These networks are over parameterized already. And that's why you can do low rank approximation quite effectively for many of them. So yeah, so what are we doing? We are representing the matrix with fewer basis vectors. And so now, my computation becomes this. Instead of becoming, multiplying something by a matrix M, I'm multiplying something by two matrices. So I'm just, absorbing these singular values into the V matrix to create this V dash. But basically, I used to have an M by N, matrix multiplication. Now I have two matrix multiplications, M by K and K by N. And so, so how do I get a speed up? It depends on K, which is also known as the rank of the matrix, or how many basis vectors I need for it. And so when do I get a speed up? So can someone kind of write an equation to reflect that speed up? What do you think? It's a rainy day, people are sleepy. Take a guess. Fine. No? Okay, that's fine. So basically it corresponds to the number of parameters or the number of remaining values in the matrix. So the ratio is m times n divided by k times m and k times n. So just adding those two numbers. So the speed up is kind of proportional to that. So keep in mind, if I do that decomposition and I don't actually remove any singular values, you're actually, you end up with a more expensive computation, right? So you need to remove a lot of those before you start getting speed up. Okay, I think we're almost out of time. But I have a friend who works on something very cool. So instead of just doing, and so he loaned me some of these slides here. But instead of kind of doing just matrix decomposition, which is what we've been doing so far, he's going a step further and doing tensor decomposition. So instead of so when I mentioned SVD, it operates on matrices and it's general for different sizes of matrices, as opposed to eigen decomposition, which is only for square matrices. But what do I do for tensors? So I can flatten the tensors and run SVD on them. That works. But you lose some information through doing that. And sometimes you need to replicate values and so on. So people now are looking to these tensor methods. And I don't kind of expect you to know everything about this in the 1 minute that I'll present this in. But this is just to give you a preview of what people are looking at now. So John is at NVIDIA now, and he's writing a library called cuTensor. So all of these tensor methods are now being written into the CUDA library as a CUDA library, and we're anticipating that they'll be very important for deep learning moving forward. And so there is a way to decompose tensors directly. One of them is called Tucker decomposition. The other one is called CP decomposition, and these are the two main ones. And you can think of them as the analog to SVD, but for higher dimensional tensors. And I'm not just talking about 3-dimensional tensors, talking about 4-dimensional, 5-dimensional, 8-dimensional, and so on. And so what do I mean by 4-dimensional? So the filters of a convolutional neural network are 4-dimensional, for example, because they're 3-dimensional, but there are many of them, depending on the number of output channels. And so, you know, your dimensions are R, S, C, and then you have K of those, right? So that's 4 dimensions. And then you can have higher dimensions as well. And so I'll run through these slides quickly, but this is kind of also a pointer to a really good paper topic, for example, if someone is interested in this kind of stuff. And yeah, so he's just highlighting here the difference between the traditional approach of flattening everything into a matrix and then doing SVD. Here we don't flatten anything, we just do the, you know, the decomposition on a tensor directly. And what does that give us? We can then compress it similar to SVD, and we can do other things to it as well. And so here is an example of compression where we're saving about 60% without losing any accuracy, and up to 80% with losing some accuracy of ResNet 101. So this is quite a good result. And so this is kind of a historical perspective when people were writing those library. BLAS is basically linear algebra library. So there's cuBLAS as well, and there is MKL-BLAS, so both for CPUs and GPUs. Basically, people started with, you know, before that there were just scalars, right? So multiplying two numbers directly. Then we had vector-vector, matrix-vector, matrix-matrix, and now we think everything will move on to tensor-tensor operations, and that's why we need those 3-dimensional transforms. Another interesting paper he worked on was this TNet, and basically what he did there was, instead of having, you know, parameter tensors for each layer, he just had one big, very high dimensional, I think it was 8-dimensional tensor here. And he used that to parameterize the whole neural network. And so what does he gain from that? He gains that, he can compress that tensor in one go. So, you know, it's compressed holistically. You can compress all the value, or you can compare the importance of all the values together through something like Tucker decomposition or CB decomposition and remove the least useful ones. And it treats the neural network as kind of one big parameterized function. And here are the parameters in that huge tensor, right? The other benefit that he found is that it actually acts as a good regularizer. And by controlling that one tensor to parameterize the whole network, he managed to get better results empirically. So, yeah, and that's kind of just generalizing that idea. Again, you can use a single tensor to train multiple models in multiple domains. And then you can then think of that tensor as a way to encapsulate all of the parameters and all of that training data in a single data structure that you can manipulate yourself. And so I'm a big fan of Jean's work, and I mean, he has a team as well now. But basically, I think this is something to keep an eye on, and it will only become more relevant moving forward. Okay, so, but back to now kind of our main topic, which is kernel implementation and approximation. So we saw different ways of implementing kernels, mainly to save on multiplications. We talked about IM2 calls, Strassens, Winograd, FFT, and log domain. And we also talked about singular value decomposition and approximating matrices, and touched upon Tucker and CP in tensor decomposition. Here are some examples of what you can read to know more about this. I also put one of Jean's papers as an optional reading if you're interested in that topic. And yeah, that's all I have today. Thanks for